Okay, thank you very much, Nicole and everybody, and good afternoon. So in this first talk, I will try to sketch a little bit the history which lead us to the experiments that discovered finally the Higgs boson. So, and I will stop then at that point. So the plan is really to set the historical context, to recall early LHC project milestones, and going back into the prehistory in a certain way. And I also want to make a clear disclaimer. Of course, I will not talk about physics, that you have heard many talks and you will get many talks as far as I understand. And I will constrain myself on hadron colliders, which finally brought us the Higgs boson. So I will not touch upon also other experiments at LHC, for example, LHCb, ALICE, which are very beautiful experiments and giving us a lot of physics. So let us start. Well, how the LHC came really about to be? Well, the community started really talking about that in 77 already. And then in 79, there was a so-called Lab White Book, which was chaired by Nino Tsikiki. And that has the sentence that the tunnel with 27 kilometers circumference and a big diameter, 5 meters, should be built in view of replacing LEP at the future stage with the proton-proton collider. But let us step back even much more. And let me recall a bit the history of hadron colliders. Actually, the first one was really the CERN intersecting storage ring, the ISR, which operated in the 70s. Then the CERN SPS P-bar-P collider, the Tevatron P-bar-P collider, and finally the LHC at CERN. There is a history written up about this in, well, about 2-3 years ago in a long CERN Courier article by Lynn Evans and myself. So let us start with the ISR. This here you see that this was a machine in the 70s with a storage ring, in fact, 2 rings, with about 940 meters circumference and with energies up to 63 GeV. And that was really a very pioneering machine. And as Lynn Evans, the machine builder, would say, this was really the groundwork for all what came afterwards in hadron colliders. Now, just for your fun, the experiments were rather simple at that time, rudimentary. In fact, you see on this picture, first of all, the 2 rings, which were separate rings, which were crossing each other then in the middle of a detector. This was experiment which was called R702. By the way, that is me 47 years ago. Now, the experiments, they were small in a way and only covered a limited solid angle. This is a sketch as shown here. I take again this experiment which I was working on with Bert Richter, who was at that time on sabbatical at CERN. The other gentleman here is Sir Chris, as he's called now, is Christopher Levlin-Smith, who later on became the CERN DG. This was an experiment to look at electron-muon coincidences because Bert was at that time saying we should find open charm. Open charm was not yet discovered. However, what was discovered was the shape psi, and I will say something about that. Now, there is a legacy from the ISR, that is the high PT phenomena. It was kind of a surprise that actually at 90 degrees there were pi zeros, as we see here on this graph, coming out at a much higher rate than what was foreseen in the current scattering models of that time. However, of course, in a way, the tragedy for the ISR was that the experiments were not really powerful enough to discover the shape psi, which could have been very well possible if one would have had a better experiments. And you can see it here on the right that in 78, we saw very clear the J and also J psi and the psi prime. The reasons was really lacking low mass electron triggers, slow data acquisition, limited solid angles. This was remedied in a way, or tried to be remedied at the end of the ISR by a very strange and unique magnet configuration, namely kind of Helmholtz coils, you see it here, which then left the 90-degree region completely free for instrumentation. So this was the first attempt to look at the 4 pi coverage. Of course, nowadays one would never do this because it blinds away all the forward directions, which are important for the physics also. So the next collider was then the CERN SPS P/P collider. This is this 7-kilometer ring. And just very briefly, the history for that machine, well, it brought in 81 unambiguous hadronic jets. They were just emerging at high PT events. Then the WZ discoveries and then searches for top, SUSY, and so on. Also a first W mass measurement. Well, again, talking about the experiments, at that time, one has learned in the sense that you need a full coverage. And this is sketched here in the case of the UA1 detector. However, it was still had one disadvantage. It was a dipole. So you see here actually the field direction of this UA1 experiment. That means particles are well deviated when they go vertical, but if they are more in the horizontal plane, then you had almost no bending power. So that's how the experiment looks like in January 81, the famous experiment of Carlo Rubbia. I was on the other experiment, which was called UA2, which had other limitations, namely it had no muon system for cost reasons. This was coming in 2 stages. The first stage was including some forward toroids together with the central calorimeter experiment, essentially, without, as I said, without any muon detection. These toroids were meant to be necessary to show actually when you would discover the W in electron-neon decay, electron-neutrino decay, to see the V-A structure. So you wanted to measure actually the sign of the electrons. Then we were told by our theory friends, well, you should just discover supersymmetry, so make it hermetic. And we built these additional calorimeters and replaced the spectrometer, which had a lot of empty space again. So, well, the success, of course, of the P/P collider were the W and Z boson discoveries in the 80s, 82, 83, and you see here Carlo Rubbia and Simon van der Meer, who then got the Nobel Prize for that. And indeed, the W here with a straight electron in the case of UA1, or a Z into E plus C minus. This is a calorimeter, electromagnetic calorimeter, rolled out from a cylinder into a plane. So you have in 580 degrees, the two electron signatures very clearly. Well, at the end, UA2 was measuring actually also not just a few Ws, but something like 2000, which were enough actually to make a measurement of the transverse mass and have a fit on the mass. And of course, well, it wasn't so bad. The result, it's still compatible with what nowadays one knows about the W mass, of course. So precision measurements started already in the UA2 area. Also at that time, one got actually 5 years before the discovery of the top quark through the theory connection with measuring the mass of the W and then standard model, one got a limit for the top quark, which was published in 92 here, and this is the value. Now, maybe I just thought I'd dig out one special slide for COMETA as you're looking at boson pairs. I think, to my knowledge, this was the first boson pair paper, experimental paper. We published 16, W gamma events. We're still a large background, but this was the first constraint really on the coupling of the W gamma couplings. So then the next generation was, of course, the Fermilab Tevatron. This is the Tevatron collider. This was just the main injector ring, which was built a bit later. And the Tevatron had a very good history, a lot of standard model physics, of course. This is the history of the runs. It did run until 2011. And there already a big step was made in constructing the detectors. These were much more detectors looking like what we would now expect from a real collider detector. So this is a sketch of CDF surrounding really the interaction point, and this is the one of D0 showing the same thing. And if you want to see pictures, that's how they look like. So much more closer to towards the LHC experiments. Now, there's one thing which one should remember from the history from CDF and D0, that they really pushed the analysis methods to a standard which was well beyond what was done at the ISR or the CERN P/P collider. This is a display of a top event from the D0 run 2. And well, the top was, of course, the major discovery at the Tevatron. This discovery was announced in a joint seminar in '95. So first time that big discoveries by two experiments were announced jointly. We will come to that, of course, for the LHC. And here are the plots, maybe not so impressive, of the top at 175 GeV, just to show. I will not go in any details, but then, of course, top physics was really done to beautiful extent at the Tevatron. This is the top signal towards the end of the Tevatron running. I think talking about the history of hadron colliders, one has at least to mention also the SSC, the superconducting super collider, which was meant to be built in Texas, near Dallas, in the 80s. The project started in 83, and it was canceled then in 93. This was something like 87-kilometer tunnel it would have had with beam energies of 20 TeV. Okay, that was, of course, a big event in the life of high-energy physics. It was too big a step, and it was not managed maybe in the way one should manage international collaborations. So let us now come to the LHC. And just as an intermezzo, I want to say LHC for some of us has also a different meaning. It was a girls' band at CERN, which I liked very much, Les Horribles Cernettes, the horrible CERN ladies, you could translate it. They did quite nice rock music and so. And you can see that they're connected to the LHC. But anyhow, let's be more serious. So actually, the idea that one could build a hadron collider and make discovery physics, that was really showcased by the UA1 and UA2 experiments. And so the CERN DG at that time in the 80s also initiated first thoughts about the hadron collider in the lab tunnel, which at that time was not yet built, but was being projected. The director, I wanted to say, was of course Herwig Schopper at that time, and just recently he had his 100th birthday. So for the community, for us, it really started, let's say, in 84 with a large workshop in Lausanne, where for the first time, concretely, we discussed the possibilities of a hadron collider in the future lab tunnel. And the name I would like to mention here is Giorgio Brianti, who was leading really the machine studies until 93. Then there were many workshops, and there was a workshop in 87, which also is quite famous. It was in La Tuile, and it was the so-called Carlo Rubbia Long-Range Planning Committee. Because also at that time, there was discussion in the community, should one build a hadron collider or a E+ E- machine? And they were already called LHC and CLIC. Of course, you can imagine I was on the side promoting a hadron collider, and we had early studies, for example, for a Higgs boson at 400 GeV. We had no clue yet where the Higgs boson would be at that time. So this would be the signal. Then finally, one was expecting in WW, and one of the W's decaying into jets and the other one leptonically. And also we had really long discussions about how one should do the experiments. And at that time also one was still writing transparencies by hand. So Carlo Rubbia wanted to build just a muon iron ball. One would have probably discovered the Higgs boson, maybe a Z prime, but not much more than that. And young guys like me and others, of course, we wanted to make a much more complete experiment. And so there were times where we were discussing this at many workshops in the community. Also, we were extremely optimistic about the time scale, because we thought, and this is a time scale which Carlo Rubbia was almost imposing us to use, namely that we would be ready with the LHC already in 98, and one had ideas that one would run commonly both LEP and LHC, alternative, of course. But okay, that idea at some point had to be, of course, to be given up. So there were other workshops. I don't want to go into that, but I think this is a bit similar what happens now, for example, for the FCC and other machines. The community came more and more together, and a decisive workshop was then in 92 in the big Evian meeting, where proto collaborations were actually presenting their ideas, and we come more and more to that now. So there were, in fact, 4 general purpose experiments which were promoted at that moment, and then also smaller experiments, for example, beauty experiments and heavy ion experiments. Well, we were talking about the paths of discovery for the Higgs boson, so I will only talk now about ATLAS and CMS at point 1 and point 5 on the LHC. And for completeness, I have put in the slides some summary table. Of course, there is no time to go into all the details of that, but it can be useful for you to see complementary approaches which were taken. I want, however, to mention the magnets. Of course, when laying out and thinking, dreaming about an experiment for a future collider, in particular in Hadron Collider, the magnet is something very special. And here we have really complementary approaches. CMS, in a way, is more simple and elegant. It has just a big solenoid, and you see here how the field looks like in a solenoid, and you know how the measurement go. Whereas ATLAS has been a bit more complex. We have a small solenoid and then a toroid where the field is like that. So the field lines in the solenoid and in the toroid, they are orthogonal. And there was a big thinking at that time that we wanted to measure muons in 2 independent ways. Because, of course, if you have a solenoid, this is all correlated, what you measure inside and eventually outside in the magnet, whereas in the iron yoke. Whereas here, of course, the bendings are orthogonal. So that was thought to be an advantage eventually. So a few pictures. This is a famous picture of CMS, where you see here the central piece, the solenoid, 3.8 Tesla. It's operated now. Initially, it was a 4 Tesla magnet. And then the iron yoke, around it, the return yoke. It is, as I said, it's elegant, has, however, constraints, of course, on the space useful for the calorimetry, both inside the coil and outside the coil. Just to give you a few impressions of how big these things were. So this is a big solenoid from CMS, which was actually tested on the surface in 2006. And the other very special thing for CMS are crystals to measure with highest energy resolution photons and electrons. And that was a big, big issue to get all these crystals built, mainly in Russia. And that was a year-long fight against time to get them in time. But they managed. something also very interesting, maybe again for future experiments. Well, CMS choose, because of the solenoid structure, you can do that, to build the experiment on the surface, and then with a gantry crane, lower it some 100 meters also almost into the underground. And that was quite spectacular operation, which was done very successfully. This you couldn't do, of course, with ATLAS because of the toroid coils. Well, finally in 2008, a nice picture of CMS when it was ready for taking data. So you see here the central part, the end cap still recessed, and that's the beam pipe. Okay, now back to ATLAS, and from now on I will be much more concentrating on the ATLAS experiment. So there were actually, as I said, 4 general purpose experiments. CMS and L3+1 were solenoids. And then there were Ascot and Eagle. We had toroid configurations. And we managed to merge the 2 experiments with the toroid configuration. That was by no means an easy thing to do, but I think we are very glad that we did that, because CMS and L3+1, they did not were not able to merge, and so the committee had to make a decision. And the decision, of course, was made for the CMS experiments, and the other ones, okay, they were the losers. Here in ATLAS, we didn't have losers. So, however, that was very difficult way, because we had, in one case, an iron toroid, in the other case, supraconducting coils, also iron in the forward backward region, essentially for cost reasons. And then going together, we figured out that we could afford a supraconducting magnet, which is, of course, superior. Just to give you an idea, after the merging, these were already quite big collaborations, something like 88 institutions and 850 authors. And this presentation was in November 92. The experiment at that stage had still a lot of options. Also, as I mentioned, this option of the toroids. For cost reasons, we wanted, for performance reasons, the supraconducting toroid. However, for cost reasons, we had to redesign it completely with less coils. Initially, it had 12 coils. And in fact, we worked out all these things and made the choices on the calorimeters and so on, which I all skipped, and then came to 2 years later to the technical proposal. And you can see in the meantime, the collaboration had really grown a lot, 240 institutions, 1,500 authors already. So the technical proposal was then presented in 95. And well, there was still a setback, because again, the experiment was too expensive. So we had to descope, and that is something which is very painful. And I'm afraid similar things will have to be suffered again by the community when it comes to the FCC detectors at some point. So we had to reduce dimensions, magnetic fields, and so on. However, I'm very glad that we resisted to too drastic descoping, because, for example, people wanted to reduce granularity of the calorimeters. Nobody at that time was thinking even of using particle flow algorithms or looking at substructures in jets or so. all this would have been impossible if we would have descoped very much the calorimeter. So, okay, that's, I think, was a lesson to learn, that one should resist too dramatic requests to descope the experiments. But of course, one has to stay within the available resources. Okay, so during this, the year 95, we had very, very intense interactions with the LHC committee. We had 6 meetings and also retreat meetings. And so that was maybe were the most intense years I have lived through. But then at the end of 95, we got finally this piece of paper, which of course you can imagine is a frame in my office, so to speak, which is a official leak by the main referees saying that they are now happy with the experiment, and that both also with CMS, and that we could go forward to work out the technical design reports, which we did over the years. In fact, there were 17 volumes of technical design reports, something like 6,440 pages. I'm not sure anybody ever read all these pages, maybe some of the main referees, but it was just impossible. But okay, that's how it went. And then the name of the game was that the experiment could be approved when the first technical design reports were approved. And these were the ones for the calorimeter. And indeed, then this happened on the 1st of July, 97, that I got this very informal letter by Chris Levin-Smith telling me that, okay, fine, now you are approved. However, of course, with a lot of milestones and things like that, and a cost ceiling of 475 million Swiss francs. So this was, these were the conditions. But of course, we were happy to go ahead. So maybe I should now step back again a couple of years and tell you what happens on the CERN side for the machine. Well, after this famous Rubia long-term planning committee, he agreed with the fact that a hadron collider is the right thing for LHC, for CERN, and he made finally council accept the statement that we should plan for the LHC. And so a proposal was then worked out for commissioning the LHC in 2002. Of course, there were agreements signed, for example, the first one, which was very important, with Russia. This is Minister Satikov signing with Carlo Rubbia the agreement that Russia would contribute to the machine. Then in 94, Chris Levin-Smith became Director General, and he presented the machine. And also there, the machine was too expensive for the member states. So he and the new project leader for the machine, Lynn Evans, they came up with an idea to build the LHC in a staged way, namely to have only 2/3 of the magnet and then straight sections. Everybody, at least the physicists, knew that this is almost impossible, but it was a good trick actually to convince council. And there is another little anecdote to be said here. Actually, council was almost convinced in June 94, but Germany and the UK not yet. So the council president, sorry, this should not be like that. The council president had a interrupted just the session, and waited until December to finish the voting, because one wanted to have unanimity, and finally this was reached in the December Council 94. So there is what the machine was approved. And then the machine was approved with the understanding that it could be the full machine if we get more contributions from non-member states. And indeed, they came, for example, from Japan. These were the first ones. Then they also came from the US. And as I mentioned, Russia was contributing, was already building parts for the LHC, for the transfer lines and so. So in 96, the machine was approved in a single stage for 14 TV with completion in 2005. Okay, so now I switch topic completely and I go a bit to the challenges of ATLAS, and I can just show you a few examples. Again, you will have time to look at this in more detail in the slides. The biggest chunk of money and the biggest engineering issue was really the toroid magnet. You see here a sketch of the barrel toroid with the barrel coils, 8 coils, and then the 2 end cap toroids. And again, just to show you, one started with small devices. This was the first racetrack coil, like they are used in the barrel toroid, was done in the late 80s to early 90s in Saclay. Then already bigger object was built in the early 90s and tested in 95, and shown that one can build coils and have them producing through superconducting cable the field one wants to have. But then there was still a long way to go, of course, to build these coils for ATLAS, which are shown here at CERN during the integration, assembly and integration. This is in hole 180. For those who know CERN, it's a big hole. These objects here are about 26 meters in this dimension, 5 meters almost in that dimension. We built these 8 coils and also tested them up to a current of 22 kiloamps, as they are used almost in the experiment. So that took over from 2001 to 2005, a long period. In the meantime, one prepared, of course, also the experimental cavern at point 1. This started in 98, the excavation. It's a cavern of 55 meters long, about 35 meters in diameter, if you want. And you see here a picture, for example, in 2003, in the beginning of 2003, during, well, it was almost finished at that moment already, but it gives you this roughly the size. There was a moment in 2003, in June, when civil engineers gave and CERN handed over the cavern to ATLAS. So this is a unique opportunity to see the ATLAS cavern empty. There was a big ceremony with the president of Switzerland, Couchepin, and the director general at that time, Luciano Maiani. And you notice some other, this was me, some other gentleman here. Another example of how it started really, I like very much this one, which is the electromagnetic liquid argon calorimeter. So in 1990, Daniel Fournier was an associate in the ATLAS group. And he had this brilliant idea how to make a fast liquid argon calorimeter. Again, I don't go into any detail, but just to show you that it started rather modestly. But so this was an engineering, as a joke, we say this is an engineering drawing of that time. But so this was in January, but already in July, we had built this little box with the accordion. And I point this out because there was a famous postdoc working very much on this device. This postdoc is called Fabiola Gianotti. So you see, working on hardware can bring you then a big career later on. So of course, this was then completed with big prototypes and so on. And finally, modules were built at several places. It's a typical module out of 32. And they were inserted into the cryostat. So all this happened from 1999 to 2004. Another thing at that time, of course, CMS, I mentioned, had these beautiful crystals, which have a very high resolution for photons and electrons. And so people were worried that maybe the liquid argon calorimeter we were designing for ATLAS, something like 10% over square root of phi, typically the resolution, would be inferior in that. However, there were ideas one could improve that by using liquid krypton, which would give you a better resolution, however, would cost a lot of money. And finally, also one has really to put into the consideration all the things, how it would work at the LHC. As I said, the crystals are beautiful for single photons, single electrons, but if you are in the environment of high luminosity, it was really shown, we could show that the resolution is marginally different. It's only maybe 7% or even less than what you have with the liquid argon calorimeter. So these were, again, slides of, by that time, no more postdoc. She was already staff from Fabiola Gianotti, proving both, on one hand, we are doing as good as CMS. On the other hand, also, it's not worthwhile spending a lot of money on liquid krypton calorimetry and then descoping the other parts. Also very important at that time was to really look at all the systematic effects during the construction. Again, I stay on the liquid argon accordion calorimeter. If these absorber plates, which are lead plates, 2.2 millimeter, if they would be not really uniform in thickness to a level of microns, 10 microns, you would really have systematic uncertainties in the energy resolution. And so it was very crucial to measure this during the construction very precisely. And we have then put sample modules in the test beam to prove that the uniformity over the barrel and end caps are really within 0.5%. 0.7% was our design goal. So a lot of effort went into this. If you make a mistake at that stage, of course, your resolution will be affected for the rest of your experiment. And we know these experiments now last for 30, 40 years. So Next milestone, 2004. We see here the liquid argon calorimeter already inserted in the cryostat, and the solenoid. We call it a small solenoid, but it's not so small after all. It's 2.5 meters and 6 meters long. 2 Tesla, which were built in Japan, and tested in Japan, was inserted. One of my favorite pictures. And finally, at the end of 2005, the barrel part with the solenoid and the hadronic calorimeter, liquid argon and hadronic calorimeter, and the toroid were installed. This was end of 2005, and this was all in place, and we could start putting the other parts. Just one picture of the hadronic end caps. Again, to give you a flavor, these were built in Russia, Germany, and in Canada, and then inserted here. And this is one of the spectacular transports. You were not supposed to shake this because it was full of electronics. So this was very gentle travel from the commissioning and integration hall, also in 180 to point 1. Took several hours. A short remark on the muon systems. There were more than 1,000 chambers built in 3 continents, pre-assembled into stations, and then this was the first one which was inserted into the magnet. So to speak, the magnet was dressed up with muon chambers. And I also like always to show these pictures. This is the end cap big wheel chambers, trigger chambers in this case, TGCs, which you see as my background at the moment. And it was really a model of working together. And we see here, for example, a happy crew from Israeli, Japanese, and Pakistani. And they were celebrating together their respective holidays and special things. I hope something which, unfortunately, today we see a bit less, of course, and I hope it will come back at some moment, that we bring really nations together and work together. Not to forget the inner detector, a marvel of technology, of course, silicon tracker, pixel detector, and special for ATLAS, the transition radiation detector during assembly. And here the whole package, this is already inside the toroid. You see here the coil and the calorimeter and being inserted the central part. Okay, that brings us then to the famous picture in February 2007 with almost everything there except for the end cap toroids. And they were also pre-assembled on site. And another picture of a rather spectacular transport. One comment on the infrastructure, which was a huge work. Just to give you an idea, there were teams of 40 technicians, engineers working over several years to put all the cables, all the pipes from the detector, route them into the counting rooms. Many of them had to be flexible because one needs to open the detector, the ones from the end caps, they need to be flexible and so on. And finally, we came in summer 2008 to this famous milestone where the last part of the beam pipe of the LHC was put into place. This really marked something like 5 years of huge work of technical coordination and so. I stress this very much because often, of course, the young people, they have not the experience of something like that. It's the mechanical part, the technical aspects, the engineering is a very big issue for getting the experiment ready. And of course, because of time, I will skip completely over the third pillar, if you want. There was the machine, there was the experiment, but the third pillar is, of course, all the computing software, which was developed in parallel, which led to the WLCG, the Worldwide LHC Computing Grid, which I think operates beautifully, which was absolutely necessary, of course, for the Higgs discovery. They have the disadvantage that one talks not sufficiently about them because they have made a system. They means, on one hand, all the computing centers, including CERN, of course, and all our colleagues in ATLAS working on data acquisition and the data flow, which I think they did a great job for that. Okay, 208-ish, that was the time with many famous visitors to ATLAS and CMS, of course, including Peter Higgs, Francois Englert, Steven Weinberg, and Stephen Hawking, who for a long time didn't believe that there would be a Higgs boson, but nevertheless, he enjoyed the visit. I said that I would say something about what you very rarely hear about. This is the part of financing the experiment. And this is controlled by what is called the Resources Review Board. They started meeting twice a year in 95, 94 already a bit. And they were really the backing for paying the experiment. And I can tell you these were really, and still are, rather dense meetings. This is the old table. It's bigger even now on the top of the main building at CERN. And these were quite nervous. You see here at that time with my management, this is Thorsten Ackerson, who was the first deputy. And so we had to defend the expenses of the experiment. And the funding agencies agreed on the best effort, in a way as gentlemen agreements in the MOUs, to make all possible to finance ATLAS. And you see here, these are all the countries in the beginning. Then there were other partners joining somewhat later. Exactly the same thing, of course, happened for the other LHC experiments. And I think we should never forget to be thankful for the agencies to pay all this. And they had to make a special effort, in fact, because remember, I said the agreement approval was at 475 million Swiss francs, 95 currency. This is the yellow bars, and that was our planning in the beginning. In red is what we actually spent, and you see we spend it slower, so you can already guess from that we were slower in building the experiment a little bit. And then there is this green part, which had a fancy name. It was called cost to completion. This was in a way just to hide the fact that the experiment did cost a little bit more, 15% or so, not tremendously more, but still, this was something like, you can see, 75 million Swiss francs. And it was not easy to convince our funding partners to come up with this additional money. But finally they did, and we can be very happy about that. So in 2008, in a way, we would have been ready to start, but then there was this famous incident. The incident happened in the connection between two dipoles, which is a very complex structure, connections of the beam pipes, of course, but then of the cooling lines, of the bus bars, and so on. And as the magnets shrink when they are cooled down, of course, they have to be flexible. And you see here, for example, some flexible connection. What happened is that one of the solders of the superconductor was not done correctly. So it lost its superconductivity, and an electrical arc developed and punctured the helium line, the helium for cooling the magnet. The helium then, when it becomes gaseous, expands a lot. And so this was the result. And that was a very disappointing result and meant some work of, 15 months of repair. So you can imagine when it came to, after 15 months in November 2009, people were very anxious what will happen when the machine would be powered on again. But everything went fine. Everybody was happy. They saw the first signs of collisions. We were happy in the control room. But the real high energy, this was at injection energy, 450 GeV on each beam, so 900 GeV. And the real high energy operation then started really on March 2010. You see here these 3.5 TV at that stage. And this was I think the machine people and Lynn Evans really deserved the toast given by Fabiola Gianotti, who was at that time then spokesperson for the successful high energy start. Just one, when these things worked, we knew in a way what we should expect as respect to the Higgs, and just one flower to the series, of course, I cannot say more. They very intensively documented and calculated what we should expect as a function of the mass of the Higgs, and at that time from already from the lab experiment, one was expecting this to be rather lowish in the maybe 130, 110 GeV range. And so these were, we knew very well what we should expect and look at. But first we had to prove actually that the experiment works. This is a slide from 2012, where we have measured standard model processes very nicely in agreement with the theory, as you can see. So we were confident things would work out. And indeed, you see on this slide the evolution of a possible Higgs signal. I point out here July 2011, the blue curve. You remember there was some excitement at some moment that there could be a Higgs at 145 GeV. But of course, a bit later on, for example, the green curve shows us that, that this went away. Evidence started building up, not yet at 5 sigma, that was in end of 2011. It was 3.5 sigma. And then the red curve was the famous 4th of July presentation in ATLAS and very similar in CMS, where both experiments reached the 5 sigma evidence. Okay, so this was the 4th of July event, both at CERN and in Melbourne. With the results were presented by Join Candela for CMS and Fabiola Cianotti for ATLAS. By the way, both were working in UA2. So you see these are when they were even much younger than on this picture. Okay, present in the audience were also Peter Higgs and Francois Englert. Just for completeness, I show you the mass peaks. That was from the presentation of ATLAS in July with 5 inverse femtobarn at 7 TeV and then 6 at 8 TeV for the 4 lepton channel and the Higgs in gamma gamma. Similarly for CMS, here I show it at the end of the run 1 with a bit more of luminosity, as you can see here. And maybe as I'm coming now to the concluding remarks, you have seen these are 2 very different experiments, different approaches, and it's, I think, very rewarding in a way that both of them observed on the same level this new particle, which at that time was called Higgs-like, but very soon, of course, its properties were clearly shown to be fully compatible with the standard model Higgs. And this is my last real transparency. In a way, it's once the machine was working, actually, this was at the end of 2012, we really reached the significance of 6 sigma much faster, means much less luminosity than what we anticipated in the physics technical design report in '99, where we thought we would need to have much more luminosity to be well above 5 sigmas. Okay, so I think the construction of the experiments, their operation and the physics analysis have been a highly rewarding time for thousands of colleagues. And the journey into new physics territory has been really fantastic and in a way continues really the fruitful tradition of exploring high energy frontier in hadron colliders. And if I can say on a personal note that I'm aware that it has been, of course, an immense privilege for me to contribute a little bit in shaping LHC and ATLAS over the 25 years which I covered in this talk until 2012. But there's still a lot of physics to come, as you know, now with run 3 and later with the high luminosity LHC and all the ambitious detector upgrades. So I wish you all the best within your COMETA network. That's it. Thank you very much.